In the previous lecture on materials for electronic components, we have covered the resistors, then types of resistors, then thermistors, types of thermistors, then VI characteristics of the resistors, thermistors, then varistors, types of the varistors, then VI characteristics of varistors and variable resistors. So this is the lecture 2 for materials for electronic components, and this is the unit 6. Now in this lecture 2 we'll cover the capacitors, right, and then inductors. So first we'll see the capacitors. So the capacitors are generally classified according to their dielectrics. And what is meant by dielectric? The dielectric which stores the energy. And there are various types of dielectrics, that is paper, mica, ceramics, etc. So the two kinds of paper capacitors are impregnated paper capacitors and metallized paper dielectric type. So what is meant by impregnated paper capacitor? So the impregnated paper capacitors are constructed by rolling paper as insulation between metal foils and filling with an impregnant. So they are relatively inexpensive and have a high capacitance to volume ratio and are capable of working at reasonably high voltage. That's why these are known as impregnated paper capacitor. Now the second one is the metallized paper dielectric type. So in metallized paper dielectric capacitors, the voids are there in between the paper and insulation, and that's why in this type of capacitor one side of the paper is metallized before rolling. Now what is meant by capacitor paper? So the manufacture of capacitors requires papers which can be used for the insulation of extremely large electrode areas at high stresses, and that's why there is a necessity for the electric strain to be high, the loss tangent to be low, and this must be independent of temperature as possible. So in addition to this, it is necessary for the paper to be of uniform known thickness and for its tensile strength to be adequate for winding under diverse conditions of tensions and width, which may range from 10 mm to 500 mm. Right, so what is the capacitor paper? So the capacitor paper is manufactured by capacitor paper is manufactured by using the papers and which can be used for insulation of extremely large electrode areas at high stresses. And what should be the conditions for that? That the electric strain to be high, loss tangent to be low, and as independent of temperature as possible. Now what is meant by loss tangent? So the loss tangent of impregnated paper is a complex function with contributions from both cellulose and impregnant. So it may be represented with reasonable accuracy, right? And that is for impregnant. So the three grades of paper are usually available, frequently designed, and that are the regular, low loss, extra, and low loss dielectric constant, and that is shown in figure, right? So A and B. So the A curve is for different type of dielectric and B is for different type of dielectric. So as per that, there is a dielectric constant on y-axis and the density on x-axis, that is depending on the type of the dielectric used. So this figure shows how the dielectric constant is related to the paper density and impregnated dielectric constant. Now we will see the electric strength and operating stresses. The electric strength of at least 150 volt per micrometer and 200 volt per micrometer are easily obtained for capacitors of about 1 microfarad with papers of thickness 8 micrometer to 20 micrometer. So the value obtained for other capacitances will be obtained by decrease of capacitance and vice versa. And that's why the unimpregnated paper gives considerably lower values. So the different types of capacitors are mica, then ceramic, glass, plastic, electrolytic, air and variable capacitors. So the figure is for ceramic dielectric capacitors. So first we will see the what is in the mica dielectric capacitor. So the main characteristics of this mica dielectric capacitor are low power factor, high voltage operation, and long-term stability at room temperature. Precision mica capacitors used as substandards and can be adjusted to better than 0.01% stability for values over 1 microfarad. So they are sealed in cases to protect against moisture. The silver mica plate capacitor has a better temperature coefficient when compared to the stacked plate type. So both types exhibit slight non-cyclic capacitance shifts during temperature variation, yielding a non-linear temperature or capacitance characteristics. Right? That is what the characteristics of temperature and capacitance. So the power factor of mica is approximately 0.0003 at 1 megahertz, but can be as low as 0.00005 when very dry, and the permittivity is around 7. Now the ceramic dielectric constant. So there are three varieties of ceramic capacitors: low permittivity, low loss types, medium permittivity, temperature compensatory types, and high permittivity types. So the constructional details of the ceramic dielectric type is shown in figure, and the low permittivity, low loss types are generally made of steatite or similar material. Steatite has a permittivity of approximately 8, and other materials may give permittivities between 6 and 15. So their high frequency performance at frequencies above 50 kHz is very good. So the power factor is reasonably low, and the temperature coefficient ranges between plus 80 to plus 120 ppm per degree Celsius. So they operate at comparatively high voltages, that is of 500 volts over a temperature from about 150 degrees Celsius down to extremely low temperatures. So these capacitors are subjected to hysteresis and accordingly are suitable for working with only very small AC voltages, and they are mainly used as bypass capacitors. Now glass dielectric capacitors. Very thin glass sheets are used to form these capacitors. The sheets are interleaved with aluminum foil and fused together to form a solid block. So these capacitors are smaller in size compared to encased mica capacitors and can be operated at very high working voltages. So their capacitance stability and quality factor Q are very constant. So since the processes in glass manufacture can be controlled accurately, a product of constant and dependable quality can be obtained. So the case of a glass capacitor is made of glass and hence quality factor is constant even at low capacitances. So these capacitances can be continuously used at high temperature up to 200 degrees Celsius. Up to 200 degrees Celsius. Now the plastic dielectric capacitor. These capacitors are characterized by high insulation resistance at room temperature. They are made of polystyrene film of polyethylene terephthalate. This type of capacitor is not generally suitable for use above 60 degrees Celsius, even though some low value capacitors are used up to 85 degrees Celsius. So the power factor, which is independent of frequency, is generally around 0.002, and its low dielectric absorption enables it to be used in long time constant circuits. So the capacitance stability should be of the order of 0.5% and permittivity is 2.5, right? Then electrolytic capacitors. The characteristics of this type of capacitor is their low volume of large capacitances, especially at low working voltage. These are suitable for use for high energy pulse storage applications, and that's why the normal types are made of plain foils of aluminum. Sprayed gauze foils or etched foils can be used to obtain large surface and hence higher capacitance. So the periodic reforming of electrolytic capacitors which are stored for a long time is essential. So the reforming is carried out by applying working voltage through a 1 kilo ohm resistor for about 1 hour. That's why the electrolytic capacitors are used for direct voltage working. The dielectric in this capacitor is aluminum oxide, which is formed by the process of electrolysis on an aluminum electron. So this electrode is called the anode because during manufacture and in use it is connected to the positive side of the voltage source. So the electrolyte used for the production of the oxide film is an aluminum borate solution. So the aluminum oxide film has a high relative permittivity and a high dielectric strength. So for these reasons the film used can be accordingly thin, which is the main reason for the high capacitance per unit of space occupied by capacitor. The electrolyte in contact with the aluminum anode oxide coating behaves as the other electrode of the capacitor. Hence, the electrolyte is also in electrical contact with an aluminum container which provides the other terminal, or with a non-oxidized aluminum which provides non-oxidized aluminum foil to which a second terminal is connected. In the rolled electrolytic capacitor, the anode consists of a long strip aluminum foil carrying the oxide film on both sides. So the ammonium borate electrolyte solution is held in an absorbent paper tissue strip of similar length. So second strip of aluminum foil with no oxide film lies next to the paper tissue and act as the cathode. So these three strips are rolled tightly together as in a rolled paper capacitor and provided with an outer cover of aluminum. So this is the electrolytic capacitor, and that's why the non-polarized electrolytic capacitor are also available for application in AC circuits without any DC polarizing voltage. So non-polar capacitor actually contains two capacitors connected in series opposing polarities. Now the air dielectric capacitors. So the air dielectric capacitors are used mainly as laboratory standards of capacitances for measurement purposes, and the insulating materials used in these capacitances is fused silica, and the whole capacitor is shielded in the metal case. Variable capacitors. For tuning receivers and low power transmitters, air dielectric capacitors are usual. A 2-gang variable capacitor suitable for use. A radio receiver contains two variable capacitors operated by a single tuning control. So in this construction, fixed metal plates or vanes connected together form a stator, and the movable vanes connected together form a rotor. So the capacitance is varied by rotating the shaft to make the rotor plates mesh with the stator plates. So the movable vanes are spaced on the spindle by spacing washers so that they do not touch the fixed vanes at the point. So the fixed vanes are insulated from the framework of the capacitor by mountings which are made of ceramic material. Full mesh of the two sets of vanes means maximum capacitance, and moving the rotor completely out of mesh provides minimum capacitance. So the vanes can be suitably shaped to determine the law of variation of capacitance with respect to the angle of rotation. Losses in such air dielectric capacitors are small, so the power factor at 1.5 MHz may be as low as 10 raised to minus 4, corresponding to a Q of 10,000. So these are the some types of the capacitors. Now the last material for electronic component is inductor. The inductors are components designed to have a specific degree of the property of inductance. Now what is meant by inductance? Inductance is the property of the material which opposes any change in the flow of current. And that's why there is a self-inductance and mutual inductance. And these inductors are used as smoothing components in power supplies, as components in filters which separate alternating currents of different frequencies, and in conjunction with capacitors to produce electrical resonance at required frequencies. So the applications of the inductors are, these are used as smoothing components in power supplies, these are also used as filters, and these are also used as components for electrical resonance at required frequencies. Now we'll see the construction. We know that inductor is what? Inductor is a core with a number of turns wounded over. So inductor is always arranged as a coil of wire. The choice of core for the coil is governed by the order of frequency of current the coil is expected to carry. And that's why for very high radio frequencies the core is simply air. Lower radio frequency inductors use a magnetic dust or ferrite core. Low frequency AC coils are inductors for smoothing of ripples in the DC output of a power unit and have a laminated core. Now the circuit symbols for various inductors are shown in figure, and these are what? With air core, then inductor with two dotted lines indicates the dust core, and only the number of turns with core, that is the iron core. So the inductance value of an inductor is generally determined by the square of the number of turns of wire used, the cross-sectional area of the core, the relative permeability of the core, and the closeness of the winding and the closeness of the winding turns. Right? Now we'll see the air core coils and core coils in one by one. Now the air core coils. So the flux leakage factor in air core coils depends especially on the air core coils, on the coil length, its radius, and the depth and number of the layers of the wire. So in air core coils the leakage flux factor is dependent especially on the air core coils, its radius, then coil length, and the depth and the number of the layer of the wire. So the inductance of an air core coil is proportional to the square of the number of turns, the diameter of the coil, and the form factor F. The form factor F is dependent on the ratio of the coil radius to the coil length plus winding depth. So here in the graph there are two curves. So on y-axis there is the leakage flux, and on x-axis there is the ratio of the coil radius R to the coil length plus the winding depth. So R is the radius of the coil, then again L indicates the length of the coil, and D indicates the winding depth. So that indicates how the leakage flux varies with respect to the form factor. Now the core coils. In high frequency ranges, coil formers may be of a ceramic material and have no core. But receiver coils in the lower region of high frequency band use cores of high permeability material, and that are classed as ferrite. A ferrite is a hard non-porous material which has the insulating ability of a ceramic but a magnetic permeability similar to a ferromagnetic material, and that's why it forms for the coils in this range may be using a plastic known as polystyrene. So whatever the forms for the coils are used in this range, that are the plastic and known as polystyrene. Now the types of the cores used for the core coils. In order to minimize losses while maintaining high flux density, the core can be made of laminated sheets insulated from each other or insulated powdered iron granules and ferrite materials can be used. So the first type of core is the laminated core, and it is shown in figure. So each laminated section is insulated by a very thin coating of iron oxide and varnish. So these insulating borders increase the resistance in the cross section of core to reduce the eddy currents but allow a low reluctance path for high flux density around the core. The transformers for audio frequencies are generally made with a laminated iron core, and the figure shows the shell type core formed with a group of individual laminations. Now second one is the powdered iron core. To reduce eddy currents in the iron core of an inductance for radio frequencies, powdered iron is generally used, and it consists of individual insulated granules present into one solid form. Next is the ferrite core. The ferrites are ceramic materials that provide high values of magnetic flux density but with the advantage of being an insulator. Therefore a ferrite core can be used in inductors for high frequencies with minimum eddy current losses. Right? So the ferrite core is what? Is a ceramic material that provides high values of magnetic flux density, but it is a insulator. Therefore a ferrite core can be used in inductance for high frequencies with minimum eddy current losses. Unit 6, that is materials for electronic components, is completed here. So the whole syllabus of the electrical engineering material course is completed, and now we are able to answer any type of question related to the materials for electronic components, that are resistors, inductors and capacitance. So thank you.